There is a place in the universe where time itself slows to nearly nothing, a boundary where the curvature of space-time becomes so extreme that light, the fastest thing that exists, can no longer move outward. Tonight, you are going there, not through imagination alone, but through the real, verified science that tells us precisely what that place is, how it was formed, and what it would mean for every second ticking forward inside you. Welcome to Quiet Science at Bedtime, a storytelling channel where every journey is grounded in real research and current scientific understanding. We are still a very new channel, and if this experience resonates with you, we would genuinely appreciate it if you subscribed, liked this video, and turned on notifications. It helps us keep making content like this, and it means more than you know. Everything you are about to hear is based on real scientific fact. Just relax and feel free to let this play as you drift off to sleep. Now imagine you are in the far future. The year has no simple number you would recognize. Time itself has become more complicated since you left the inner solar system. You were aboard a research vessel called the Penrose, named after the British mathematician Roger Penrose, who in 1965 proved mathematically that singularities, points of infinite density, must form inside black holes under very general conditions. The ship was built to operate within extreme gravitational gradients, its hull reinforced with materials engineered at the atomic scale, its instruments calibrated to detect changes in gravitational field strength to 1 part in 10 to the 15th. You have been traveling for what the ship's clock reads as 4 months. Earth's clock reads differently. You have not checked by how much. Ahead of you, approximately 1,200 kilometers in closing, is a stellar mass black hole. Its designation in the ship's catalog is unremarkable. What is remarkable is its existence and the fact that you are here, close enough to study it with your own eyes. This black hole was once a star, a massive, luminous star with an original mass estimated at approximately 50 to 60 times the mass of the Sun. Stars in this mass range burn through their hydrogen fuel rapidly. Where the Sun has a main sequence lifespan of roughly 10 billion years, a star of this mass lives for only 3 to 5 million years before exhausting its core hydrogen. You are looking at something that was a furiously burning star during a period when the earliest complex multicellular life was just beginning to develop on Earth. When the fusion reactions in its core finally slowed and could no longer provide the outward pressure to counteract gravity, the star collapsed inward in a fraction of a second. The outer layers exploded outward in a core collapse supernova, an event that briefly radiates as much energy as the Sun will emit in its entire 10 billion year lifetime. The core, compressed beyond the density of an atomic nucleus, could not stabilize as a neutron star. It continued collapsing until space-time itself closed over it, forming what general relativity describes as a singularity, a point of curvature so extreme that our current mathematics breaks down. What remained was this: not nothing, something far stranger than nothing. You look out the forward viewport. Space is visibly distorted. The stars behind the black hole are not where they appear to be. Light from those background stars is traveling through what should be a straight path through vacuum, and in a sense it still is. Light always follows the straightest possible path through space-time, but space-time near the black hole is not flat. It is curved, bent by the black hole's mass according to Einstein's field equations of general relativity, first published in November 1915. The curvature redirects those light paths, shifting the apparent positions of background stars, stretching some into arcs, creating multiple images of the same object on different sides of the black hole. This effect is called gravitational lensing, and it was first confirmed observationally during the total solar eclipse of May 29th, 1919. British astronomer Arthur Eddington measured the apparent positions of stars near the edge of the sun's disk and found they were displaced by approximately 1.75 arcseconds, exactly matching Einstein's prediction. That measurement, made on a small island in the Gulf of Guinea off the coast of West Africa, changed the course of scientific history. What you are seeing now is that same effect, operating at a scale Eddington could not have dreamed of. The black hole ahead of you does not appear as pure darkness. It appears as an absence ringed by light. The accretion disk, a flat structure of superheated gas and plasma spiraling inward from the surrounding space, glows, not in the warm orange of a flame, but in the hard blue-white of plasma heated to temperatures exceeding 10 million degrees Kelvin in its inner regions. The disk emits X-rays, ultraviolet radiation, and visible light simultaneously. The radiation pressure from the disk is intense enough that your ship's instruments have been recalibrated to account for it. The black shadow at the center of that glowing ring is called the black hole shadow. Its angular size depends on both the mass of the black hole and your distance from it. At your current distance, it subtends an angle large enough to resolve clearly with the naked eye, something no human being has ever experienced looking at a real black hole before this mission. You leave the ship. You are in a pressure suit engineered for extended exposure in this environment. It maintains your body at standard atmospheric pressure, 101.3 kilopascals, and regulates your oxygen partial pressure at 21 kilopascals. Your suit has its own atomic clock, synchronized with the ship's master reference before you departed the airlock. The two clocks are currently showing the same time. That will change. As you move closer, something becomes apparent that no diagram or simulation fully prepared you for. The black hole shadow is growing, not because you are moving quickly. Your approach velocity is careful, measured, slow. It is growing because you are moving into a region where the geometry of space itself is compressed. Distances are not what they appear to be from far away. The metric tensor, the mathematical object that defines distances in curved spacetime, changes value as you descend into the gravitational well at a distance of approximately 1.5 times the Schwarzschild radius. You enter a region called the photon sphere. The Schwarzschild radius of this black hole, the radius of its event horizon, is approximately 68 kilometers. That figure comes from Carl Schwarzschild's exact solution to Einstein's field equations, derived in 1916. The formula is elegant. The Schwarzschild radius equals 2 times the gravitational constant times the mass divided by the square of the speed of light. For this black hole, at 23 solar masses, that gives a radius of 68 kilometers. The photon sphere sits at 1.5 times that value, at approximately 102 kilometers from the center. This is the boundary at which light can travel in a circular orbit around the black hole. A photon entering this region at exactly the right angle will circle the black hole indefinitely, trapped in a perpetual orbit. The orbit is unstable. Any perturbation will send the photon either spiraling outward and escaping, or spiraling inward and falling past the event horizon forever. If you were to look sideways at exactly this distance, you would see the back of your own head. Light from your suit has traveled outward, curved around the black hole, and returned to your eyes from the opposite direction, completing a circle of pure physics. You pass through the photon sphere. Below you, approximately 136 kilometers away, is the event horizon. Here is where the science becomes something you feel in your body rather than only process in your mind. In 1915, Einstein's general theory of relativity did something no prior theory of gravity had done. It described gravity not as a force transmitted through space between two masses, but as a consequence of curvature in space-time itself. Mass and energy curve the four-dimensional fabric of space-time, and objects follow the straightest possible paths, called geodesics, through that curved geometry. What we experience as the pull of gravity is actually the curvature of space-time, directing objects along those geodesics. The critical implication for time is this: time is not a separate stage on which physics plays out. Time is a dimension of space-time. When space-time curves, time curves with it. The deeper you are in a gravitational well, the closer you are to a massive object, the slower time passes for you relative to someone far from that object. This is called gravitational time dilation. It is not philosophical. It is not metaphorical. It is a measured, verified, practically important physical phenomenon. In 1959, physicists Robert Pound and Glenn Rebka measured gravitational time dilation over a vertical distance of 22.5 meters using gamma rays in a Harvard laboratory. They confirmed that a clock at the bottom of the Jefferson Physical Laboratory Tower ran slower than a clock at the top by a factor consistent with general relativity's prediction. In 2010, physicists at the National Institute of Standards and Technology measured time dilation over a vertical separation of just 33 centimeters, approximately 1 foot, using aluminum-ion atomic clocks accurate to 1 second in 3.7 billion years. The clock 33 centimeters lower ran slower by approximately 4 parts in 10 to the power of 17 per second. This is a real, measured effect operating right now between the floor and the ceiling of any room on Earth. Near this black hole, the effect is not measured in parts per 10 to the 17th. It is profound. The Schwarzschild metric, the equation that describes the curvature of space-time outside a non-rotating spherically symmetric black hole, gives us a precise relationship between your position and the rate at which your clock runs relative to a distant observer. At the innermost stable circular orbit, which sits at 3 Schwarzschild radii from the center, at approximately 204 kilometers from this black hole's center, your clock runs measurably slower than the ship's clock. For every minute that passes on your suit clock right now, more than a minute is passing on the ship. The closer you descend to the event horizon, the more extreme this ratio becomes. At a distance of 1.01 times the Schwarzschild radius, a mere 0.6 of a kilometer above the event horizon, your clock would run more than 7 times slower than a clock at the photon sphere. At 1.001 times the Schwarzschild radius, the ratio exceeds 22 to 1. At the event horizon itself, the ratio becomes infinite. From the perspective of a distant observer, a clock at the event horizon appears to stop entirely. The event horizon is not merely a boundary in space, it is a boundary in time. You are not falling, you are hovering, but even hovering here, in this gravitational field, time is moving differently for you than it is for anyone who is not here. This is a physical fact about the universe that existed before any human mind conceived it. You check your instruments. You are at approximately 3 Schwarzschild radii from the center, at the innermost stable circular orbit, which is the closest stable orbit possible around this black hole. Below this boundary, no stable circular orbit exists. A spacecraft attempting to maintain a circular orbit at 2 Schwarzschild radii or closer would need to apply continuous thrust to avoid spiraling inward. The mathematics of general relativity leaves no room for negotiation on this point. You are aware of a faint, subtle sensation across your body, a differential. Your feet, oriented slightly closer to the black hole than your head, are experiencing a fractionally stronger gravitational pull. The difference in gravitational force between one end of your body and the other is called a tidal force, and it arises because gravity obeys an inverse square law. The force changes with the square of the distance, meaning even a small change in distance produces a measurable change in force when the gravitational field is this steep. Tidal forces are what drive the tides of Earth's oceans. The side of Earth facing the moon is pulled toward the moon more strongly than Earth's center, and the center more strongly than the far side, producing the characteristic bulge that follows the moon around the planet. The same principle, scaled to extremity, operates here. For a stellar mass black hole of this size, the tidal force gradient near the event horizon is lethal. A human body would be stretched and compressed, a process physicists have named spaghettification, by tidal gradients that exceed any material's tensile strength. This stretching would begin well outside the event horizon for a stellar mass black hole, which is why this mission maintains a minimum safe distance. The physics is different for supermassive black holes. The larger the black hole, the more gradual the tidal gradient near the event horizon, because the horizon is farther from the singularity. For a black hole like Messier 87 star, the one imaged by the Event Horizon Telescope collaboration in April 2019, the event horizon has a radius of approximately 19 billion kilometers. That is roughly 2,000 times the distance from Earth to the Sun. The tidal force gradient at that horizon is gentle enough that a human body could, in principle, cross it without immediately experiencing fatal forces. You would be inside the black hole before you felt the danger. Messier 87 star, located approximately 55 million light-years from Earth in the Virgo cluster of galaxies, has a mass of 6.5 billion solar masses. The image of it published in April 2019 was constructed using the Event Horizon Telescope, a network of 8 synchronized radio telescope arrays spanning the diameter of the Earth, from Hawaii to the South Pole, achieving an effective angular resolution of roughly 20 microarcseconds. This is equivalent to reading a newspaper in New York from a sidewalk cafe in Paris. The bright ring in that image is produced by synchrotron radiation, photons emitted by electrons, spiraling at relativistic speeds, in the magnetic field threading the accretion disk. The black hole in front of you is far smaller, but it is equally exact. 10. You hold your position at the innermost stable circular orbit. You look inward at the event horizon. The boundary in front of you is not a physical surface. There is no wall, no membrane, no material of any kind. It is a geometric threshold, a surface defined entirely by the mathematics of curved spacetime. Specifically, it is the surface at which the curvature of spacetime is so extreme that all future-directed paths, all geodesics, whether through space or through time alone, point inward. At the event horizon, there is no direction that leads outward, not because something is blocking the way, but because space-time itself is flowing inward, faster than light can travel outward. This concept requires a careful understanding. In flat space-time, far from any mass, you always have a choice of direction. You can move in any spatial direction, and time always flows forward. But space-time curvature affects the structure of those choices. Near a black hole, the inward directions begin to dominate, closing off more and more of the available future. At the event horizon, the last outward direction closes. All futures lead to the singularity. The first person to describe this mathematically was Carl Schwarzschild, who derived the exact solution to Einstein's equations for a spherically symmetric, non-rotating mass in December 1915, just weeks after Einstein published the field equations. Schwarzschild was serving as an artillery officer on the Eastern Front during the First World War When he found the solution, he sent it to Einstein by post. Einstein presented it to the Prussian Academy of Sciences in January 1916. Schwarzschild died in May of that year from a rare autoimmune disease contracted at the front. He was 42 years old. He never knew that his equations described objects that actually exist across the universe. That is the weight of what you are looking at, a boundary described by a letter sent from a war, by a man who did not survive to see what he had found. In 1974, Stephen Hawking brought together two frameworks of physics that do not yet fully agree with each other: general relativity and quantum field theory, and derived one of the most surprising predictions in 20th century physics. Black holes, he argued, are not perfectly black. Quantum field theory tells us that the vacuum of space is not empty. At the quantum mechanical level, the vacuum is filled with fluctuating fields from which pairs of virtual particles, a particle and its antiparticle, spontaneously appear and then almost immediately annihilate each other, returning their borrowed energy to the vacuum. This process happens everywhere in space, all the time, entirely within the limits of Heisenberg's uncertainty principle, which permits temporary violations of energy conservation for extremely short intervals. Near a black hole's event horizon, Hawking argued, this process can be interrupted. If a virtual particle pair appears with one particle just inside the horizon and one just outside, they cannot annihilate. The inner particle falls toward the singularity. The outer particle escapes. To a distant observer, it appears as if the black hole has emitted a real particle, carrying real energy away from the black hole. This emission is called Hawking radiation, and it is thermal. It has a temperature, now called the Hawking temperature. For this black hole, at 23 solar masses, the Hawking temperature is approximately 12 billionths of a Kelvin, 12 nanokelvin. The cosmic microwave background radiation that fills all of space has a temperature of 2.725 Kelvin. The black hole is colder than the space around it by a factor of more than 200 million. Therefore, it absorbs far more background radiation than it emits. It is gaining mass, not losing it. Only in a future so distant it defies conceptualization, after the cosmic microwave background has cooled below 12 billionths of a Kelvin, which will occur on a timescale on the order of 10 to the power of 67 years, will this black hole begin to evaporate faster than it absorbs. The current age of the universe is approximately 13.8 billion years, which is 10 to the power of 10 years. The evaporation timescale exceeds that by 57 orders of magnitude. You are standing near an object that will outlive every star currently burning in the observable universe, every star, every galaxy, every stellar remnant. This black hole will still exist when the universe has reached a degree of cold and darkness that has no name in any human language. And you are floating here, 68 kilometers above its event horizon, on the suit's instruments and the math of Einstein, watching it simply be. The tether begins its retraction now. Gentle, measured, the ship is calling you back. You begin to rise. The tidal force differential across your body eases as you ascend. The gradient decreases with the inverse cube of your distance from the center, which is why the sensation fades continuously rather than abruptly. The mathematics of tidal forces is precise. They scale with the derivative of the gravitational field rather than the field itself, and so they fall off faster with distance than the gravitational force does. You watch the event horizon as you rise. The ring of light does not disappear immediately. Even at 5 times the Schwarzschild radius, the bending of light paths is visible. The accretion disk's near side is brighter than its far side, an effect called relativistic beaming, caused by the Doppler boosting of photons emitted by plasma moving toward you at a significant fraction of the speed of light. The far side of the disk is dimmer, its photons Doppler shifted to lower energies as that plasma moves away. The asymmetry in brightness is not an artifact of your instruments. It is a direct visual signature of plasma moving at relativistic velocities in a strong gravitational field. Your suit clock reads 17 minutes and 42 seconds since you left the airlock. You return to the ship and connect the instruments. The ship's clock has advanced by 21 minutes and 8 seconds. The discrepancy is small, 3 minutes and 26 seconds over a period of less than 20 minutes. But it is real, measurable, verifiable. You aged 3.5 minutes less than the ship during your excursion. You are, in the most literal physical sense, 3.5 minutes younger than you would have been had you remained aboard. Not by metaphor, by physics. The airlock closes behind you. Pressure equalizes at 101 kilopascals. You remove your helmet. The air inside the ship smells of recycled atmosphere, slightly metallic, slightly neutral, but it is breathable and warm. You find your bunk, you lie down. The ship's environmental controls maintain an interior temperature of 19 degrees Celsius. This is deliberate. Sleep research, including foundational studies conducted at Stanford University and the Netherlands Institute for Neuroscience, indicates that the optimal ambient temperature for sleep onset in most adults falls between 16 and 20 degrees Celsius. This is because your body requires a reduction in core temperature of approximately 1 to 2 degrees Celsius for sleep to begin effectively. A cool ambient environment supports this process by allowing excess body heat to radiate outward through the skin. There is a precise physiological mechanism at work. Your body's circadian rhythm is governed by a structure in the hypothalamus called the suprachiasmatic nucleus, a cluster of approximately 20,000 neurons that functions as a master biological clock, coordinating timing signals across every organ system. In the evening, whether on Earth or in a ship with a simulated light-dark cycle, the suprachiasmatic nucleus signals the pineal gland to begin releasing melatonin into the bloodstream. The pineal gland is a small, pinecone-shaped structure located near the center of the brain, roughly 8 millimeters long and weighing approximately 150 milligrams. Melatonin itself does not cause sleep directly. It does not act as a sedative. It acts as a hormonal signal, a chemical broadcast to the body's tissues, announcing that darkness has arrived and that the biological conditions for sleep are now appropriate. Your pineal gland is doing that now. Somewhere in your brain, deeper than thought, the transition has begun. Stage 1 of non-REM sleep represents the threshold between wakefulness and sleep. It is typically brief, lasting between 1 and 7 minutes in most adults. During this stage, your brain's electrical activity transitions from the beta waves of active waking cognition, which oscillate between 13 and 30 hertz, through the slower alpha waves of relaxed wakefulness at 8 to 12 hertz, and into the theta waves of light sleep at 4 to 8 hertz. This transition is not sharp, it is gradual, like a tide coming in rather than a wave breaking. Your muscles relax in sequence as the descending motor pathways from your cortex become less active. The muscle tone you carry throughout waking hours, a constant low-level electrical activation in your skeletal muscle that keeps you upright and ready to move, gradually releases, sometimes just at the edge of stage 1 sleep. The brain produces a hypnic jerk, a sudden brief muscle contraction that startles you back to wakefulness. This occurs in approximately 70% of people and is thought to result from a misfiring of the motor system during the transition, possibly an evolutionary remnant of an ancient reflex that prevented sleeping primates from falling from tree branches. The science of the hypnic jerk is not fully resolved, but its frequency, its timing at sleep onset, and its universality across human populations are well documented. If it happens, it is not a problem. It is simply your motor system releasing its grip. Let it go. The black hole outside the viewport has not changed. It does not respond to your presence. Its event horizon is exactly 68 kilometers in radius, as it has been for the millions of years since this object formed, as it will be for the unimaginable future during which it persists. The accretion disk continues its rotation. The photon sphere traps its circling photons. The Hawking radiation continues at 12 billionths of a Kelvin. The universe is very good at persisting without being observed. Stage 2 of non-REM sleep begins. Your brain now produces bursts of activity called sleep spindles, rhythmic oscillations at 12 to 15 hertz, lasting between half a second and 3 seconds, generated by thalamocortical circuits involving the thalamus and the cerebral cortex. The thalamus, a roughly walnut-sized structure positioned near the center of the brain, normally functions as the brain's primary sensory relay station, routing visual, auditory, and somatosensory information from the body to the appropriate cortical areas for processing. During sleep, the thalamus shifts its activity pattern to produce spindles instead, effectively gating sensory information before it can disrupt sleep. This is why sounds that would wake you if you were drowsy may not wake you during stage 2 sleep. The thalamus is actively filtering them. Sleep spindles have been associated in the research literature with the offline consolidation of declarative memory, the type of memory that stores facts and events. As you descended toward that event horizon, as you watched the accretion disk and measured the time dilation and saw the distorted stars, your brain was encoding all of it into working memory. In stage 2 sleep, the first pass of consolidation is beginning. Patterns of neural activity replayed in compressed form, strengthening the synaptic connections that will eventually make those memories retrievable. Your brain is filing away what you saw. Deep sleep is approaching now. Your breathing has slowed further. Each breath takes longer than the last. In stage 3 non-REM sleep, also called slow wave sleep, the delta waves dominate. Delta oscillations fall below 4 hertz, sometimes as slow as 1 cycle per second. The brain's electrical activity reaches its most synchronized state of the night, with large populations of neurons firing together in slow, rolling waves that can be measured at the surface of the scalp with millimeter electrodes. During slow wave sleep, your pituitary gland, a structure roughly the size of a pea attached to the base of the brain by a thin stalk, releases growth hormone into the bloodstream. In adults, growth hormone no longer drives height increases, but it continues to regulate protein synthesis and the repair of damaged tissue throughout the body. Approximately 70% of the daily growth hormone secretion in adults occurs during the first slow wave sleep episode of the night. Your body is repairing itself right now at the cellular level. There is also the glymphatic system to consider, described in the scientific literature for the first time in 2012 by a research group led by Macon Nettergaard at the University of Rochester. The glymphatic system is a network of fluid channels surrounding the blood vessels of the brain that functions as the brain's waste clearance system. During slow wave sleep, brain cells, primarily astrocytes, shrink by up to 60% of their waking volume. This shrinkage dramatically increases the space between cells, allowing cerebrospinal fluid to flow more freely through the brain tissue, flushing out metabolic waste products that have accumulated during waking hours. One of the waste products cleared most effectively by glymphatic flow during sleep is beta amyloid, a protein whose accumulation in the brain is associated with the progressive neurodegeneration of Alzheimer's disease. Sleep does not merely rest the brain. Sleep actively cleans it. This has been happening every night of your life. Tonight, in a ship 1,200 kilometers from a black hole, it is happening again. Outside, the accretion disk continues its work. The plasma in the disk, primarily ionized hydrogen and helium, with trace elements depending on the composition of whatever material has been captured over the black hole's history, orbits at speeds approaching a significant fraction of the speed of light in the innermost regions. As the plasma spirals inward past the innermost stable circular orbit, it has no stable orbit left to maintain. It accelerates toward the event horizon, compressing and heating as it goes. Just before crossing the boundary, it radiates most of its remaining energy as X-rays. Approximately 6% of the rest mass energy of infalling matter is radiated in this process, a conversion efficiency far greater than nuclear fusion, which converts about 0.7% of hydrogen's rest mass to energy. The accretion process around black holes is one of the most energy-efficient processes in the known universe. The photons from that disk left their source and traveled outward at 299,792,458 meters per second. They passed through the intense gravitational field near the black hole, some of them lensed into circular paths, some escaping outward, eventually reaching your ship's instruments. Those measurements are stored in the ship's database now. They will be transmitted back to Earth, where radio signals traveling at the same speed of light will carry them across whatever distance separates the system from the Sun. Scientists on Earth will reconstruct the spectrum, identify the emission lines, and learn something about the plasma conditions in the accretion disk of a stellar mass black hole studied at closer range than any instrument has achieved before. Science does not stop when you fall asleep. There is a concept in physics called entropy. In thermodynamics, entropy is a measure of the number of microscopic configurations, the number of possible arrangements of particles and energy that correspond to a given macroscopic state. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time. Disorder accumulates, organized structures dissipate, energy spreads out. Black holes present a deep puzzle in this framework. When matter falls into a black hole, what happens to its entropy, its information? The laws of quantum mechanics state that information cannot be destroyed, that the quantum state of any system, even a complex one, must in principle be recoverable from the final state of the system. But a black hole absorbs information and, at least classically, never releases it. The event horizon is a one-way surface. This is the black hole information paradox, and it remains one of the most actively debated unsolved problems in theoretical physics. Stephen Hawking's discovery of Hawking radiation changed the nature of the paradox. If the black hole slowly evaporates, perhaps the information is encoded in the radiation. But the mechanism by which this could occur is not yet understood. The Hawking radiation produced by any standard analysis appears to be purely thermal, carrying no information about what fell in. Physicists, including Juan Maldacena, with his anti-de Sitter space and conformal field theory correspondence, derived in 1997, have argued that black holes must be consistent with quantum unitarity, that information is preserved. But the exact mechanism remains open. You are near the horizon of this paradox in the literal sense, not just the scientific one, the boundary of what the universe is willing to tell us. Your breathing is very slow now. In slow-wave sleep, the average adult takes approximately 12 to 14 breaths per minute, compared to 16 to 20 breaths per minute during quiet waking. Each breath moves a tidal volume of approximately 500 milliliters of air in and out of the lungs. The diaphragm contracts, flattening downward by 1 to 2 centimeters, expanding the thoracic cavity and reducing intrapulmonary pressure below atmospheric by approximately 1 to 2 millimeters of mercury. Air flows in along that pressure gradient, the alveoli, tiny air sacs in the lungs, with a total surface area of roughly 70 to 100 square meters in an adult, exchange oxygen and carbon dioxide across membranes approximately 1 micrometer thick. Oxygen molecules cross into the capillaries, bind to hemoglobin molecules in red blood cells at 4 binding sites per molecule, and are carried through the pulmonary veins to the left ventricle of the heart, which pumps them outward through the systemic circulation. Red blood cells spend approximately 25 seconds completing one full circuit of the body. In slow-wave sleep, your heart rate has dropped, somewhere between 45 and 60 beats per minute, depending on your cardiovascular baseline. Each beat moves approximately 70 milliliters of blood. Over the course of tonight's 8 hours, your heart will beat somewhere between 21 and 28,000 times, moving roughly 1,500 to 2,000 liters of blood, without a single voluntary instruction from your conscious mind. Your body knows exactly what it is doing. The ship is quiet, the instruments are steady, the black hole outside occupies its fixed position in space, bending and redirecting everything around it, without effort, without intention, without any of the qualities we use to describe deliberate action. It simply is. There is a broader context worth holding as you rest. The black hole outside is not unique. The observable universe, the sphere of space-time from which light has had time to reach us since the Big Bang, approximately 93 billion light-years in diameter, contains an estimated 100 billion galaxies. Each large galaxy hosts at least one supermassive black hole at its center. The Milky Way's central black hole, Sagittarius A*, has a mass of approximately 4 million solar masses and an event horizon radius of roughly 12 million kilometers, about 17 times the radius of the Sun. Astronomers have tracked the orbits of stars near Sagittarius A* for decades, using infrared observatories that can peer through the dense dust clouds of the galactic center. The star known as S2 orbits the galactic center at a maximum speed of approximately 3% the speed of light, completing one orbit every 15.9 years. Its orbital precession, a slow rotation of the orbit's orientation in space, was confirmed in 2020 to match exactly the prediction of general relativity. Every year, S2 completes another fraction of its orbit. Every year, measurements confirm that a 4 million solar mass black hole sits at the orbit's focus. The science accumulates, one observation at a time, one clock comparison at a time, one gravitational lens at a time. Knowledge is not an act of imagination. It is an act of measurement, repeated and refined, carried forward across generations. Your first REM sleep episode is approaching. REM, rapid eye movement sleep, was first systematically identified in 1953 by Nathaniel Kleitman and his graduate student Eugene Oserinsky at the University of Chicago. They observed that sleeping subjects exhibited periodic episodes of rapid, conjugate eye movements beneath closed eyelids, accompanied by a brainwave pattern closely resembling the low-amplitude, high-frequency activity of wakefulness. This finding was counterintuitive. Why would a sleeping brain produce near-waking electrical activity? The paradox deepened when researchers confirmed that dreaming, in most people, occurred predominantly during these periods. During REM sleep, the brainstem structures that generate the paradoxical cortical activation also suppress voluntary muscle movement, producing a condition called REM atonia. Specific neurons in the ventromedial medulla and the spinal cord actively hyperpolarize the motor neurons that control skeletal muscle, preventing you from acting out the motor sequences your dreaming brain is generating. The muscles of your eyes are exempt from this suppression, hence their rapid movements. Diaphragm activity continues, but most voluntary muscles are effectively paralyzed during REM. This suppression is not failure. It is precision. It is the brainstem keeping you safe from the contents of your own dream. You may dream of what you have seen, of the ring of light that hangs against the dark, of the precise mathematics of the photon sphere, the careful measurement of a time difference between two clocks, of standing at the innermost stable orbit and looking inward at a boundary defined entirely by the curvature of space. If you do, that is not fantasy. That is physics, processed by a dreaming brain, retained in the consolidating networks of slow wave and REM sleep, and made available for the rest of your life as genuine understanding. You saw something real tonight. Your body moves through the first REM episode and back into slow wave sleep again. This is normal. A typical night of sleep consists of 4 to 6 sleep cycles, each lasting approximately 90 minutes, with each cycle moving through stages 1, 2, 3, and then into REM and back again. The proportion of slow wave sleep is highest in the first half of the night. The proportion of REM sleep is highest in the second half, with the final REM episode of the night sometimes lasting up to an hour. Your brain is following this rhythm. It has been calibrated to this rhythm by millions of years of evolutionary history, by selection pressures acting on every generation of your ancestors, by the rotation of a planet on its axis, and the daily alternation of light and dark that shaped the circadian biology of nearly every organism on Earth. Sleep is not a modern invention. The oldest fossils of animals with recognizable sleep behavior date back hundreds of millions of years. Even invertebrates, organisms separated from your lineage by more than 500 million years of evolution, show behavioral states that appear homologous to sleep, complete with reduced responsiveness to stimuli, characteristic postures, and homeostatic pressure that increases with deprivation. The universe did not begin with sleep, but life, almost as soon as it became complex enough, began to rest. There is something in that worth carrying into the night. The delta waves are deepening again as you enter another slow wave episode. Your brain is synchronized, the thalamus is filtering, the glymphatic flow is active, growth hormone is being released in pulses from the pituitary. Everything is working. Outside, 1,200 kilometers from the ship's hull, the black hole exists as it always has. Its Hawking temperature remains 12 billionths of a Kelvin. Its event horizon sits exactly at 68 kilometers. The accretion disk continues its luminous rotation, the innermost plasma orbiting at close to half the speed of light, the outer plasma orbiting more slowly, the whole structure governed by the Keplerian dynamics of gravitational orbital mechanics, modified by relativistic corrections. The frame dragging effect, the lens Thirring effect, named for physicists Joseph Lenz and Hans Thirring, who predicted it in 1918 from Einstein's equations, continues to pull the surrounding spacetime slightly around the black hole's axis of rotation. Even the vacuum is not still here. The rotation of the black hole's mass drags spacetime itself around with it, a consequence of the off-diagonal terms in the Kerr metric, derived in 1963. Frame dragging is not metaphor. It has been measured in Earth orbit by the Gravity Probe B experiment, launched in 2004, which detected the frame dragging effect of Earth's rotation on a set of gyroscopes orbiting at an altitude of 640 kilometers, confirming it to within a few percent of the general relativistic prediction. Even the Earth is doing this, rotating, dragging spacetime, pulling the vacuum along its axis, by an amount 43 orders of magnitude smaller than the black hole outside, but by the same physics, the same equations, the same universe. You are very quiet now. Your eyelids do not move. Your breathing is slow and regular. The muscles of your face carry no expression. Your blood pressure has dropped to its lowest point of the day. Your cortisol levels, the primary stress hormone secreted by the adrenal glands atop your kidneys, which normally begins rising in the hours before dawn to prepare you for wakefulness, are at their daily minimum. There is nothing for your body to defend against right now. There is nothing for your mind to solve. The black hole outside will be there tomorrow. The accretion disk will still glow. The time dilation data will still be in the instruments. The Penrose will maintain its orbit. The mathematics of general relativity will remain exactly as Einstein left them in November 1915, as Schwarzschild elaborated them in December of the same year, as generations of physicists have tested and confirmed them in the 111 years since. The science is not going anywhere. You are allowed to sleep. Let your awareness rest now, not drift away. Rest, like an instrument powered down after a careful measurement. The data is recorded. The clocks have been compared. The numbers have been noted. Stage 3, delta waves. Your brain is washing itself. Your growth hormone is releasing. Your immune cells are active and patrolling. Your memories of the ring of light are being filed. The physics of the photon sphere recorded. The sensation of time moving differently for you than for the ship encoded. It will all be there when you wake. For now, the distance between you and the event horizon is 1,200 kilometers, and increasing as the ship's orbit carries you slowly, safely away from the innermost approach. The tidal forces on your body are negligible at this distance. The gravitational time dilation is detectable only with atomic clocks, not with any subjective sensation. You are ordinary again. Ordinary in the most extraordinary setting. And ordinary is exactly right for sleep. The ship moves through its orbit. The black hole turns in its own ancient rhythm. The cosmic microwave background radiation, the thermal afterglow of the Big Bang, emitted approximately 380,000 years after the universe began, when the temperature dropped below 3,000 Kelvin and hydrogen atoms first formed, and the universe became transparent to light for the first time, fills the space in all directions with photons at 2.725 Kelvin. These photons were produced when the universe was a fraction of its current size. They have been traveling since then, stretched by the expansion of space from wavelengths in the near infrared to wavelengths in the microwave range, arriving from every direction simultaneously, bathing everything in the universe in the same faint thermal glow. They pass through the hull of this ship. They pass through you. They have been passing through every structure on Earth for the entire history of life. The energy they carry is negligible, but they are the oldest light in the universe, and they are here with you right now, in this bunk, in this orbit, in this quietly extraordinary night. You do not need to hold on to any of it. Let the physics persist on its own, as it always has. If you are still awake to hear these words, then here is what we hope you take with you into sleep. You visited the edge of a stellar mass black hole tonight. You stood at the innermost stable circular orbit of a space-time geometry, described first in a letter sent from a war. You measured the difference between two clocks separated by a gravitational well. You learned that time is not absolute, that it flows at different rates depending on where you are in the universe's curvature, and that this is not philosophy, but measurement. You learned that the event horizon is not darkness. It is a geometric fact, a boundary defined by an equation. You learned that your body, while you sleep, clears its waste, repairs its cells, consolidates its memories, and releases the hormones it needs to face tomorrow. That this process has been happening in your ancestors for hundreds of millions of years. That it will happen in you tonight without any conscious effort from you. All you have to do is be still. If this journey brought you something, stillness, wonder, peace, or simply the weight of closed eyelids, we hope you will come back. Quiet Science at Bedtime is still a new channel. Every subscription, every like, every notification turned on is a direct and meaningful act of support that allows us to keep building these journeys, long, slow, scientifically grounded stories through the most extraordinary places the known universe has to offer. If you are still awake enough to hear this, thank you. Please subscribe. Please leave a like. Turn on notifications so the next journey finds you when you need it. And if you are already asleep, then this found you exactly when it was supposed to. Sleep well. The black hole is still out there, patient, ancient, and precisely described by the mathematics of a century ago. The universe is extraordinary. You already know that. Your body is doing everything it is supposed to do. The rest is silence. Good night.